In the previous videos, we saw that the activity coefficient, plays a very important role in quantifying the non-idealities of a liquid mixture. And in the context of vapor-liquid equilibrium, those non-idealities will also affect the pressures and compositions we're going to see in the vapor phase. And so it's important for us to have a good way of calculating what gamma I is. And from the definition of gamma I, we know that it's just equal to the exponential of the partial molar Gibbs excess energy. And then if we kind of rearrange the equation, we can see that the natural log of gamma I is just equal to the partial molar Gibbs excess energy, or this. Okay? And so if we want to have a good way of calculating gamma I, that means we also need to have a good model for our excess Gibbs energy. And so, similar to when we discussed our various pressure, volume, temperature equations of states, there's also lots of different models for the molar Gibbs excess energy. So there are different models for Gibbs excess. Or another way you could think of this is that for the Gibbs excess, what you're looking at is not pressure, volume, temperature models or equations of state, but you're looking at chemical potential, temperature, mole fraction equations of state. Okay? All right, and so what I want to discuss in this video is just various models that people have developed for the excess Gibbs energy. Now, experimentally, when people have set out to measure the molar Gibbs excess, in particular for binary mixtures, what they observed is this, is that the molar Gibbs excess energy divided by not only RT, but also the mole fraction at species 1 and mole fractions at species 2, they've observed that this sort of ratio is linear with x1. Okay? All right. And so, based on that experimental observation, the scientist Margulies proposed this model. Completely spell that. Proposed this model, where this ratio here was going to be equal to this model here on the right, where we have A21 x1 plus A12 x2, where these A's are coefficients, I'll say. I'm not using the word constants, but I'm using the word coefficients. Okay, so in any case, the right-hand side would have that form, or if you take advantage of the fact that x2 is just 1 minus x1, you could rearrange the equation like this. Okay. And so these A2 and A1 terms, those are the Margulies coefficients, named after Marguli. And the advantage of writing the equation in this format is now you haven't, as I mentioned here, experimentally they've observed that this ratio is linear with x1. In this format, you now have a mx plus b equation, right? Where this is your slope and this is your intercept. And so if you did an experiment where you measured this and then you made a plot where this was the y-axis and this was the x-axis, the slope would give you this and the y-intercept would give you that, right? So that's the advantage of plotting the data in that way. Okay. In any case, so we have this is equal to this. But if we want to calculate GI bar, we need to take the partial derivative of GXS. Okay. So now let's rearrange the equation. So that we have GXS over RT is equal to x1 times x2 a21 minus a12 x1 plus a12. All right, and we know that if we want to calculate our activity coefficient, which is related to the partial molar Gibbs energy via this relationship, we would just plug in this equation into here. Okay. Oh, there's an RT missing. All right. Okay, and so this is constant temperature, pressure, J not equal to I. Okay. And so to evaluate this derivative, you just need to remember a few things for this derivative. That the total N is equal to N1 plus N2. Your mole fraction X1 is equal to N1 over N1 plus N2. And then X2 is similar. Okay. And so if you apply all these relationships and actually go through with the partial derivatives, you will get these two sets of equations. Or this set of equation, I guess. Where ln of gamma 1 is equal to x2 squared a12 plus 2 a21 minus a12 x1, and then ln of gamma 2 is equal to x1 squared a21 plus 2 a12 minus a21 times x2. And this set of equations for the different activity coefficients, these are known as the Margulies equations. Okay. All right, and so this set of equations here is what you could use to calculate your different activity coefficients. Okay. Now the reason I was adamant that these are coefficients and not constants, I want to make a couple of comments about them. So generally, for the full Margulies equation, a12 is not equal to a21. They're going to be two distinct values. And also, I want to say that these things are also functions of temperature. So your a12 has this form, where they're like inversely related to temperature. And this up here, this is a constant. Okay. And then for a21, it'll have this form. All right, and so that's kind of the first Margulies equation that was developed. But there are some systems where parameter. So in very special cases, there are some systems where a12 is equal to a21, and then you could just call that A. And so for this one parameter version of the Margulies equation, which you can kind of think of like the ideal gas version of the Margulies equation, or of our GXS models, molar GXS over RT would just be equal to x1 times x2 times A. Okay. So that would be the one parameter version. Okay, and so this here were examples of the Margulies equations, which once again are just models for this excess molar Gibbs energy. But those aren't the only models that exist. And so for the last few parts of this video, I just want to tell you what other models are. Another model out there is called the Van Laar model. And the way that this model was developed, it's actually based on the van der Waals gas equation of state, specifically the molecular interaction terms in there, the A and the B constants. And so the Van Laar model is a more kind of molecular model for the molar Gibbs excess equation. In any case, for the Van Laar model, it is a bit more complicated than the Margulies equations. And so it has this form, where I'm using these primes to show that these are separate from the Margulies equation, or these are different from the Margulies equations. A21 prime x2. And so this is the model for the excess molar Gibbs energy. And if you went out and did the partial derivatives, you would get that the activity coefficients are equal to this. 1 plus A12 ln of gamma 2 is equal to A21 prime 1 plus A21 prime x2 divided by A12 prime x1, also raised to the negative 2. Okay. All right, so the Van Laar model is just another example, another model for describing the excess molar Gibbs energy. But Margulies and the Van Laar aren't the only ones out there, and so the other ones that exist include, there's many out there. There's an almost infinite amount out there, but some other common ones that you'll encounter, not only in thermo, but in your separations class, include the regular solution theory, and then there are more kind of sophisticated, more modern ones, like unifac, uniquac, and for polymer systems, the most famous of these excess Gibbs energy equations is Flory-Huggins theory. So for those that are interested in polymers, you'll hear about this equation a lot. Oh, I meant to write for polymers.